Okay, this is Physics 1C for September 3rd. We're talking about flux and Gauss's law tonight. So, I need to, oops. Okay, you guys should be able to hear me now. So we're talking about flux, and we're talking about Gauss's law. I introduced flux last time. I'm just going to kind of reintroduce what it is for you guys real quick. Flux is the idea that if I've got an area where I've got some electric fields, let's say you've got some electric field lines like this. Apologize for the sloppiness. It takes a while to get used to this each time. And within that region of space, if you place like some type of a surface, these are often just imaginary surfaces. Sometimes they're real surfaces, like the surface of a conductor, for example. Then what we do is we can say that you can define a flux by assigning an area vector to your surface, like this. The area vector points perpendicular to the surface, and the magnitude of it is equal to the area of the surface itself. And then in general, we can define the flux for a constant, basically you'd say like a smoothly shaped object that's flat with a constant electric field as being, you take the electric field, you take the dot product with the area. What that amounts to being is E times A, the electric field times the area, and then multiplied by the cosine between the two of them. Okay? That's pretty much it. It's not necessarily all that complicated. The possibility of having the angle shows up whenever the surface you're talking about, let's say you have a surface that you're looking at the edge of the surface here, so the surface goes into the plane of the page. You would draw a vector for the area that would point perpendicular to the surface, and then we need to extend this line here. If that's the electric fields, the angle theta is the angle between the two of them right there. And flux is a scalar. It also, usually we put an E down here for flux. Because there's two types of flux in this class. There's going to be electric flux, and there's also going to be magnetic flux. Okay. The other possibility is you have some type of a surface that's not flat. So for example, you could have a sphere. This is one of the first things that we're going to look at. So suppose you have a sphere, and you want to talk about flux through the sphere. And so you put, for example, let's say you have a positive charge in here. And we know that that positive charge produces field lines that branch out from the charge. Now, if we make the sphere so that it's completely centered on the charge Q, then we know that these field lines will automatically be at a right angle to the surface, like this here. And in order to describe what happens here is you have to basically break up the surface. Let's use a different color. You have to break up your surface into little pieces. And those pieces we call dA. Imagine taking like a very tiny piece of Scotch tape and putting it on a balloon. Okay? You know, if like you take a square of Scotch tape and you put it on a balloon, that's what this little dA is going to be. It's just it's an area element of your surface. And the direction that the vector for that would point would be perpendicular to the surface, which is going to end up being parallel to those field lines. And if you do this, then we can describe the electric flux through this surface by using a surface integral. And that's what we'll do today to solve some problems. Okay? This is how we define the flux in a scenario like this. And I will look at some examples pretty quickly here where we apply this. So that's our goal here. We're going to start off by talking about flux in this form, and eventually we want to develop flux in this form. And then finally what we want to do is we want to connect the flux to the charge that's here to talk about what's called Gauss's law. All right. So let us look at an example problem where we can apply flux like this. So this one is a pretty straightforward problem. We want to find the flux through a cube. Okay. So it says, consider a uniform electric field E oriented in the x direction in empty space. So you have a field, it points in the x direction. We could easily write that in terms of symbols like this. This electric field could have some value. It could be like 100 newtons per coulomb, multiplied by I hat if we want to. But the electric field only points in the x direction, okay? So a cube of edge length L is placed in the field, oriented as shown. Now there's a picture for this, but we're just going to draw a picture, because the picture has all kinds of information on it that I want to kind of draw for you. So we're going to start off with an XYZ coordinate system here. Make it black. Within this coordinate system, we're going to put a cube. Cube like right at the corner of this. Oh, I need to make this so it's kind of parallel here, don't I? What if I go like that? Will that help? That's a good enough cube. Tried to line it perfect, but I didn't quite get it, did I? So you have an electric field. It points only in the x direction, so we need some vectors to represent that. Let's use red for that, I guess. Say red, and then it just doesn't. We'll just, that's probably good enough, right? We'll just use those for our electric field. It only points in the x direction. I could stagger these, but it might make the picture more cluttered. Anyway, so we've got electric field represented there. Now we can start drawing. So our electric field is given here. I'll make it clear that's electric field by doing this. We've got a box, and our goal is to figure out the flux through this cube, and it has sides of length L. Okay, so this side is L, that side's L. They're all the sides are L. Alright, so let's go through and talk about what the flux for each of these pieces is going to be. We're going to look at each face of the cube, basically, and talk about flux. So let's talk about the front face of the cube here. On the front face of the cube, this is a closed surface, the cube is, right? So when we define our area vectors for our cube, the way that we're going to do that is they're going to be pointing out of the surface, not into the surface. So that's going to be what an area vector looks like for this face of the cube here. So I'm going to label that as A, like that. And let's pick some values for these things so we can actually get numbers too. So let's say the length per side of our cube is like 5 meters. Okay, can anyone tell me, based on our definition of flux, where flux is equal to E dot A, the electric field dotted with the area, what would the flux through the right surface be in this case? Am I looking at the wrong chat? I knew it. I'm so sorry. Let's catch up here. I gotta stop doing that. Okay. EL squared. There you go. The same amount enters and exits. That's right, Ash. Okay. So through this face, the area is L squared, right? The electric field is E. And the angle between the two of them is what? The area vector and the electric field. What's the angle? Yeah. Okay. So the flux through that face, maybe we label this face number 1 or something. We say flux 1 is equal to EL squared. It's still doing ink to shape. I really don't want it to do ink to shape. Undo. There we go. So we'll call it phi 1 and say that's just EL squared. Or in terms of the numbers that we have here, what would that be? It'd be 100 times 25, so it'd be 2500. And it's a scalar, okay? What about the top surface right here? We'll call that surface 2. What would the flux through the top surface be? How do I draw the area vector on the top surface? Do I draw down into the cube, or do I draw it up away from the cube? That's right. So our area vector here is going to point like this. What's the angle then between that area vector and the electric field? 90. So what's the flux through phase 2 going to be? Or through the top. We'll call it the top, maybe. That's even easier. It's going to be 0, right? Any other faces through which the flux is going to be 0? Bottom. Yeah, what else? On the bottom, we draw the area vector down. Again, when there's a closed surface, you always draw your area vectors out of the surface. So the bottom is going to be 0. Any other faces that it's going to be 0? Really, the question is, do any of the field lines... Remember, this is one of the things we said yesterday. Flux is basically proportional to the number of lines that actually go through your surface. So do any of the field lines cross through the top? No. Bottom? No. What other surfaces do the field lines not cross through? Side. Well, there's 4 sides. The front and back. There you go. So if I drew an area vector for the front, it would point out like that. And if I did an area vector for the back, it would point back that way. And the angle between... Did it do shape again? Whatever. This is supposed to be an A. So the front face, electric field and area are at right angles to each other. Back face, electric field and area are at right angles to each other. So no field lines actually go through there. So you could say phi through front is 0, and flux through the back is 0, and through the bottom. Okay, so far it's just the front face, or the right face that we're calling 1 over here. So what about the back face? What direction would I draw the area vector for the back space? The back face. No, not back. Left. We'll call it left. What is the flux through the... Or which direction do I... Yeah, okay. The area vector points back this way. The electric field is represented by that red line, right? So we know at that location, we can put them back to back, that the electric field goes this way, right? God, writing on this is getting bad. So what's the angle between the electric field and the area vector then? It's 180 degrees, right? So we multiply by cosine 180 degrees, and the only difference between the right and the left is that you get negative EL squared. Now this tells you some things that I haven't mentioned yet about flux, but maybe you already figured it out, which is that flux can be positive or negative. It's generally negative when the field lines are going into your surface. It's generally positive when the field lines are going out of the surface, right? So flux in is negative, and flux out is positive. Positive. And that's pretty much all there is for this problem, except that it also asks us to find the net electric flux through the surface of the cube. And what's the net electric flux going to be? It's 0. That's right. You get the same amount through the front. As many lines come in as go out, which I think is the first thing that Ash said, the same amount enters and exits. That's an indication that the net flux through your surface is 0. If every field line that goes in also comes out, you're going to get 0 flux. Okay? The only way to have a positive flux or a negative flux total would be to have a source of an electric field inside of the box itself, such as a charge. A charge is a source of an electric field. It's like a sprinkler that shoots out electric field lines all around it. A negative charge is like a sink that draws in electric field lines all towards it. This is the only way to get non-zero net flux. If all your field lines are external, you're going to get 0 flux. And that's that. Do you guys have any questions? You can try this with different shapes too if you want to. This shape is pretty trivial, but we could replace the triangle that's here with any shape that you want. You could put like a triangular prism in here, for example, like the equal angle, equilateral triangular prism in here, and you could prove that you get the same situation that occurs. You could throw a sphere in here, actually. It'd be a lot more complicated, right? Like, suppose that we draw some sphere or something inside of this, or even an oval. And it's, we say specifically that it's a... We say specific... Okay, really? We're just going to have to do something like that first. Okay. We say we've got our little oblong, like, egg shape here, right? And I want to figure out what the net flux through this object is. I can say without calculating it that the net flux through this thing is going to be 0. But if you cut it in half and you try to figure out how much flux comes in one side versus the other side, it's going to get a little trickier, right? Can you guys see why? At every point on the surface, you're going to have very strange angles for your calculations, right? We would call these all DAs. And you would need to integrate over the surface of this object if you truly wanted to figure out what the flux through each individual part is. But you can say without question that the net flux is 0, which often is all we really care about, as you'll find out. Okay? Does anyone have any questions? You guys have a problem very similar to what we did here, by the way, on your homework, except that there's a function for the electric field, which is going to make it so that the value of the electric field on one side is different than the value on the other. And as a result, the calculation is just a little trickier, but it's not that hard. Are there any points on the sphere that don't have flux, or is it similar to the cube? I would say right here, at the bottom, there'd be 1 point. There'd be 1 point exactly. And right here on the top. It's a little different than the cube because you've got like a whole big surface through which there's no flux. But for this, it would really just be 1 point, so that's kind of meaningless. That's a good question, though. Now, the front and the back, you'd have negative flux coming in here on the left side, and then positive flux going on the right side. That's where you have the maximum flux, actually, would be right here and here. Oh, front and back. You're right. My bad. Like the close side and the far side. Yep. Absolutely, that's right. All right, that's a simple flux problem. Let's do something here now. So let's say that we take, this is going to be basically Gauss's law. We want to kind of derive, in a way, Gauss's law. So how do we do that? So what we're going to do is we're going to do exactly what I said at the beginning of class. We're going to start with a point charge. We're going to say it's a positive point charge Q. We're saying that this point charge it's a point. Okay, so I'm going to draw a dot for it, and around that dot we're gonna construct a sphere. It's not a real sphere; it's an imaginary sphere. Does it look like a circle? Kind of. Right about there. And then we'll draw some three-dimensional stuff to make it kind of look like a sphere for a second. I could do this with another shape, maybe. Here we go. So there's our sphere. I can do more. We're not going to. Okay. So we've got a sphere, and let's make it a different color too. And inside of our sphere is a point charge Q. And what we want to do is to find the net flux through this object, just like what we did. Now, it's a curved object, though, so the way we have to do that is by starting with the definition of flux that says that flux is equal to this integral over a surface of E dot dA. And because we're going through a closed surface, I'm going to put a little circle here to say that we're going to perform this evaluation, this E dot dA, over the entire surface. Okay, what does this mean? This means that every location on my sphere, I need to choose the point. At that location, I need to draw the direction of the electric field. You guys tell me, if I come to this point, what I've chosen right here, what direction does the electric field point? Does it point at an angle, like, tangent to the thing? Does it point at a right angle? Does it point in? What is it? Which way does it go? Out of the sphere? You mean perpendicular, right? Yeah. So, at this location, you're going to have an electric field, and it's going to point that way, right? That's your electric field right there. And I'll just label that as E. The next thing that we have to do is we have to, on our surface, we need to break our surface up into little pieces. Like I said, imagine like taking some Scotch tape and putting it on a balloon. There's a little patch there. And that patch that you've chosen, it has a area vector associated with it. And that's the dA part of this. So you guys tell me, what direction would the area vector for this little patch that I chose here point? Is it going to be at right angles to the electric field, parallel to the electric field? Also perpendicular to the surface, which is going to end up being parallel to the field, right? So let's drop in here a line like that, and just indicate these two lines are basically coincident with each other, right? So we're going to define that one. I want to get rid of this piece right here. Just want to write here, this is our dA, right? Now, just to be clear, I think I can say with confidence, and hopefully you guys agree with me, any point that I pick on my sphere, exactly the same situation would occur, right? So I pick another point on the opposite side, right? We come over here, for example. Every point, and this is the value of what I've chosen here, is I've chosen a sphere that's made it so that the electric field is right at the center, right? And since the electric field lines for this object always point away from the center, we know that another point over here, you'd have an electric field vector that would point like that, and it would be perpendicular to the surface, and then we could also have our dA vector pointing exactly at the same. And really what we're looking at is the dA at the location. The dA is just, it's a surface element, right? It's a surface element, and over here it's gonna point parallel as well. Okay, so every point on the sphere that we choose, these two things, there's several things that are gonna be true. The electric field will always be parallel to the surface. dA is the surface at a point, basically. But in addition, how will the electric field here compare to the electric field here? If I tell you that the radius of this sphere is little r, how does the electric field compare at each of these two locations? They don't exactly cancel out, do they? Not that they cancel out. One is up and to the right, the other one's up and to the left. And I chose them at arbitrary points, so... What about the value of the electric field at those two locations? Will they be the same? They have the same radius. Yep, this is r out to here, and that's also r out to there. The E is the same, right? So for both of these two E's, I wrote them as E, and they mean the same thing. We know for both of those what the value of the electric field is, right? We know that at any point on a sphere of radius r surrounding a charge, the electric field will be the same. It's going to be k times q, the charge at the center, divided by r squared. At every point on the surface, that's the value of our electric field, okay? Okay, so now is where we actually do the integral, and I'll talk about what we're doing when we do this integral. Our next job is to take the quantity E times dA and add it up for every single portion of the surface, right? Imagine enclosing the entire sphere with a grid. You mark it up with the grid lines, right? And you got to calculate this quantity, E, times dA at every point. And you ask, what is dA? Well, dA would just be some tiny little amount. It'd be something like, you know, dA could be something like, I don't know, 1 times 10 to the negative 10 meters squared or something like that. You could break up your object up into how many ever parts it took. How would you know? Well, you need to know the radius. Let's say the radius is like 2 meters, right? And then you say, okay, 2 meters, that's going to have a surface area of 4 pi r squared. That surface area we could break up into this many parts. And then we would just find the value of the electric field at each one of those and do a sum. That's literally what we're doing here, is we're going to do a sum of E times dA for every single point. And the, what's the word for it? The precision of the sum that we do is going to be dependent on how small we make our little cuts dA. Does that make sense to you guys? Don't think of it as an integral. Just think of it as you're doing a sum of E times dA for every single point, okay? And we could literally do it numerically if we want to. And I guarantee you we would get a really, really close to the same answer as we're going to get. Now, we don't even need to do that, though. We can be much simpler. We can evaluate this very simply due to basically the fact that it's a very symmetric situation. I could rotate this sphere any way I want to, and it's not going to change the way that it looks, right? As long as I keep the center of the sphere right there. And keep in mind, this sphere that I've drawn is just some imaginary surface, by the way. It's not a real surface. Okay? It's just some, I mean, obviously it's not real. It's on a computer and it's whatever. But you're viewing the sphere, right? It's just, it's an imaginary surface. Only imaginary, not in the sense that it's not real, but just in the sense that you have to kind of picture in your brain what this thing is. In fact, what we're going to do is we're going to give a name to this type of surface, this imaginary surface. We're going to call it something. We're going to call it a Gaussian surface. Okay? We're going to call it a Gaussian surface. All right, so let's look at how we do these integrals. And I'm going to emphasize that the way I do this integral this time will be almost exactly the same as what you will do every single time. Okay? Except one difference is going to be that you're not going to know E. We know E. So we're going to do this a little bit differently. The first thing I'm going to say is that we noticed that at every point on our surface, E and dA are parallel to each other. What is the angle between E and dA? Here. It's 0, right? So we can replace E dot dA with simply E times dA and then a cosine theta. Right? Now, what else could we do? So, our electric field vector right here, right? We said already that as I move from point to point to point, there is no change in the electric field as I move across that surface, right? There's no change. So what we can do is we can take the electric field and we can just pull it out of the integral. Because the electric field has the same value at every single point on the surface. It would have a different value if our surface was, say, curved outward in some way, right? If a piece of our surface were to protrude out like this in some way, then the electric field would be different here versus here, and we'd have to do some integration along this strange-looking curve here. Does that make sense? We don't have to do that. Every point has the same value for the electric field. How many things do I need to undo to get it off? Every point has the same value, therefore it doesn't vary with respect to the surface, so you just pull it out. Oh, and I shouldn't have said cosine theta right here. That's my bad. It's not cosine theta, right? It's cosine 0. I mean, you could have an angle theta, but in this case it's 0. So now, I mean, what do we do now? I mean, now it just says the integral over a closed surface of dA. What do you guys think that means? If you saw that, what would that mean? dA is just going to become A, but now which A are we talking about now, though? Is it the area of a square? Is it the area? What is it going to be the area of? It's a surface area. This was, after all, it was a surface integral, so it's the area of the surface, which is a sphere. You guys are saying it properly in chat there. That's great. So now we just get E, and we think, okay, what's the area of a sphere? It's got to have a pi in there, right? And it's area, so there's some r squared, but then there's another factor. What is it? No, it's area. It's not r cubed. It's a 4. That's right. That is the surface area of a sphere. And this is something you're going to see show up a lot in these problems that you do. So you might want to reorient yourself with surface areas of cylinders and spheres if you don't remember them. Okay, well now we go to the final step wherein everything gets really simple. So what was the electric field? Well, it was this. It was K times Q over r squared. But we actually have a different way of writing it that happens to be kind of neater in this one. So we're going to do that. We can replace K here with 1 over 4 pi epsilon naught, right? You guys remember that? And why did I choose to do that? Well, I noticed there's a 4 pi here, so I think that it might look nicer if we just put in 1 over 4 pi epsilon naught like this, and then put in Q. We divide by r squared, and that's multiplied by 4 pi r squared, and lo and behold, the r squareds cancel, which is kind of surprising, maybe. Maybe not, I don't know. And all we have left over is this very simple relationship, an incredibly simple relationship, that's something that we intuitively came to last time by just considering what flux was. And we figured out that it doesn't matter how big of a surface you make around our charge, you actually get the same flux. You guys remember we were talking about that last time? That I could have made the size of my radius of my sphere here twice as big, and I would still have gotten the same flux, right? Because the radius canceled out. I could have drawn a box around this, and I would have gotten the same answer anyway. This tells us Gauss's law, basically. It says that if I have a closed surface, the flux through that surface is directly proportional to the charge inside. Usually the way this is written is like charge enclosed, where Q enclosed represents the amount of charge that's actually within the surface. I took the version of this that's in, I don't know, your textbook or another textbook, and I just I copied it here, just to make sure that I'm being clear about what Gauss's law states, and I'll repaste it for you guys here. So this is the statement of Gauss's law from a textbook. I can't remember which one it was. It says, now, we did this for a sphere, and so you might think, oh, this only works out like this for a sphere, but you can prove that this works like this for any type of surface that you choose. And the general statement is that the net flux through any closed surface surrounding a point charge q is given by q over epsilon naught and is independent of the shape of that surface. So that means that our surface could even be something very strange, something complicated. Like maybe our surface is like really weird. Okay, a surface can't have little holes like this. We can't. you can't have little loops. I'll take that part out. But yeah. So suppose that was our surface. We call it surface 2 or something like that. And I ask, okay, what's the flux through surface 2? And the answer is it, first you have to see, is it closed surface? And I say, okay, yeah, this surface actually comes out of the screen. You're just seeing one piece of it. But the answer is still, it's just going to be whatever that charge is divided by epsilon naught. Closed. It doesn't have to be a simple surface. Okay, simple surface. Yeah, you're right. Sorry, that's the correction that I was making there without. Yeah. And that's pretty powerful because now what we can do is there's another piece to this, which is now we connect back to this statement right here and say, okay, so not only is flux charge enclosed, but then, and this is the really cool thing about it, is you say the flux is equal to q over epsilon naught, but that's kind of less important than the fact that this is now directly related to the electric field, right? This is kind of the equation version of Gauss's law in what we call integral form. There's another version of Gauss's law we'll learn later. I need to write it down for you if you want me to. But this now relates the charge to the electric field, kind of in a different way. And what's powerful here is we can use this to find electric fields. That's what we're going to use it to do. We're going to look at some situations that we've kind of already looked at, and we'll go ahead and readdress them with Gauss's law. And then what you'll find is you're able to kind of do more difficult problems with Gauss's law. But that's it, basically. The net flux through any closed surface surrounding a point charge q is given by q over epsilon naught. Not only that, but I want to, and I'll answer your question here in a second, Ash, about the differential version. Not only is the net flux given by that, but suppose that I take, for example, and I'll pick some really simple numbers here. Let's say I have a charge of 2 coulombs right here, and next to it I have a charge of negative 1 coulombs, and down here I have a charge of, I don't know, up here maybe, let's say we've got a charge right here of negative 7 coulombs, okay? And I give you some kind of different surfaces, right? I say, okay, suppose that I surround these guys with a surface like this, and again, I'm only going to draw it two-dimensionally, and I ask the question, what's the flux through this surface? And you say, well, I know that the flux for just the negative 7 coulombs would be 7 coulombs divided by epsilon naught, and for the 2 it'd be 2. But this flux thing is a scalar, so it doesn't even matter where these charges are located. It just doesn't matter at all. All you need to do is to just sum up all the charges, so negative 7, negative 8, plus 2 is going to be negative 6, and I say that if we saw the surface S1 or something, that the flux through 1 is just going to be, what did we say? It's negative 6, right? Negative 6 coulombs divided by epsilon naught. Right? And if I chose a different surface, like if I instead said, okay, well, what if I just pick these two pieces right here, and I have a closed surface, and I say I call that surface S2, I would say the flux through 2, you guys tell me what would it be? What's the flux through surface 2? It's 1 coulomb divided by the constant, right? And the constant's just whatever. In certain systems of units, we could just make that constant equal 1 if we want to. So, one thing that's really interesting about this is you might ask, okay, well, what about this negative 7 coulombs right here, right? Well, it certainly has its own electric field lines, right? Like, for example, it would have an electric field line that would point like this, and it would have an electric field line that would point like that, and like that. I'm kind of like messing up here, but you guys get the idea. This thing has electric field lines. This is just for the 7 coulomb charge, right? Call it E7 or something like that, right? But you notice that it doesn't impact that surface, and why is that, Ash? Because the same amount enters and leaves, right? Any piece that we can find that enters also exits. And because flux is all about the number of lines, you can see that there's the net flux due to that guy is 0, right? It's just like the problem we did just a second ago, where, now think about this, like, electric fields come from somewhere, right? I mean, we have this problem, we just say, okay, here's our electric field, but certainly that's coming from somewhere, right? You can actually reverse this situation. I can ask a question about the problem we just did. How much charge is inside this box? The net flux was 0. So how much charge is inside the box? There's none. There's no way there's any charge in there, because if there was, this wouldn't be true, right? You have to have charge to have flux. It's required. And I think that the homework problem that I gave you guys, what you do is you find out there is a net flux, and you use the flux to figure out how much charge is in the box, which is pretty powerful. Okay, Ash wanted me to write down what the differential version is, and I'll just say in as few words as I can without introducing anything that's too crazy, that there's this thing you can do in calculus wherein you take kind of a three-dimensional version of an integral, of a derivative. It's called a gradient, and it involves an operator, and the operator kind of looks like this in Cartesian coordinates. If you don't understand what I'm doing right now, I'll try to explain it. These are what are called partial derivatives. They're kind of similar to normal derivatives. It's the normal xyz you might know about, the ijk you normally know about, right? And there's an operation that you can do with these things on vector fields, where you take a dot product with this. This is, after all, it's a vector. It has ijk's, so you can basically dot product it with something like an electric field. And what happens is that if the electric field has components in the x, y, and z direction, that this thing becomes this. We call this operator we call it divergence. The operator itself is called the del operator or nobla. There's all kinds of different names for it. But there's a particular one wherein you basically take the spatial derivative of each component. So this is e, x, y, z, and z. So basically what you end up doing is you take the partial of the x component of the electric field with respect to x. So you're looking at the way in which the x component of the electric field changes in the x direction. You're looking at the way in which the y component changes in the y direction, and the way in which the z component changes in the z direction. This produces a scalar, and you can prove using some theorems, well, we'll prove this in about 10 weeks or so, that this ends up being equal to the charge density divided by epsilon naught. This is the differential form of Gauss's law. Yeah, it's like the gradient vector. This is not the Laplace. Laplacian is another operation. Laplacian is what you get when you do nobla dot nobla, or del dot del. And that gives you the second derivative operator, which is nobla squared. That's the Laplacian. This is called divergence. This thing is usually called del operator or nobla, I think. Nobla? I don't know if that's right. I don't know. There's all these weird names for it, but whatever. It's like the gradient, though, as Jesus said. Okay, that's just an aside. Someone asked a question, I thought I'd answer it. This is the other version of Gauss's law. This is the version that shows up on the classroom in Physics 1C in the front of the room. There's a big set of this is the first Maxwell equation, by the way. We've learned it today. It's called Gauss's law, but this is number one of the Maxwell equations. It defines everything we need to know about what's called electrostatics, that is to say, static charges, systems like that. But this is the first Maxwell equation. You can tell your parents or your friends or whatever. You started learning Maxwell's equations today, and Gauss's law is the first one. Okay. Yeah, Gauss's law restates Coulomb's law. That's right. It's basically a restatement of Coulomb's law in a more kind of general form that's even more powerful. Now, what we want to do now, okay, I never know which one the best one to start with is here. We can do this. This is a good thing to do, and then we'll probably do this one problem here, and then we'll stop. So this is kind of an example problem. It's not really an example problem. It's more like a quick quiz, actually. Something I want you guys to think about. You can answer in the chat if you want to. Okay, but before we do that, actually, did you guys have any questions? I'm going kind of fast. Any questions? Feel like you're gaining an understanding for what flux is, hopefully. Inherently connected to charges. All right, so, yeah, read the problem. It says, a spherical Gaussian surface surrounds a point charge Q. Describe what happens to the total flux through the surface if A, the charge is tripled, B, the radius of the sphere is doubled, C, the surface is changed to a cube, and D, the charge is moved to another location inside the surface. I'll maybe draw each of these. So your basic setup is this. Point charge Q, surrounded by a sphere, right? This is your initial setup. Let's get some sphere. And be careful about it. Don't answer too quickly, guys. I want to do this like one at a time. Let's do part A first. It says, what happens to the total flux through the surface? So we say this surface, we say the flux we know is equal to Q over epsilon naught, right? Part A says, what happens to the total flux if the charge is tripled? So if Q goes to 3Q, but nothing else changes. So your system is just 3Q. Okay, the flux triples. You guys got that fast. Yeah, so the flux, God, I hate drawing the symbol, goes to 3 phi. So 3 times the flux. Yep. Part B, what happens if the radius of the sphere is doubled? So now what happens is you just got the same charge, but your sphere is bigger. What happens to the flux here? Nothing. Stays the same. Right? Size of the sphere has no effect on the flux. Part C, the surface is changed to a cube. What happens now? Just put it in a box. Again, nothing. This one is weird because if you try to think too hard, I hate, when I was studying this stuff originally, I was like, but it's so weird because the field lines here are nice and simple, but what about these field lines that cut through the corners? Like, that's complicated, you know? But it doesn't matter. At the end of the day, it all works out, and the flux stays the same. The cube doesn't matter. Finally, D says, what happens if the charge is moved to another location inside the same surface? So let's be really extreme about this. Suppose that I move my charge right here. Okay, and again, no change. It's the same. It doesn't matter where it is. It doesn't matter that there's going to be a bunch of field lines dense over here and a bunch of field lines that are separate over here. The electric field here is going to be really strong, but it's a tiny surface over which it's strong. Over here, the electric field's weaker, but it's a big surface, right? So you get a trade-off there, basically, and you get the exact same flux. There you have it. I think that's a really good problem, especially when you're first learning this stuff, to kind of just verify for you guys that you believe and understand what's being said. All right. Now we will do one that is a little more challenging. Here. That's the answer. We'll leave that for the end. All right. Ooh, I thought that was going to do both. Just want to scale both these up just a little bit. Nope. Gotta do it one at a time. Alright. This problem is going to introduce some notation and words that it's definitely useful for you guys to get to know. So what we have here is an insulating solid sphere of radius A. Okay. There's already some words in there that are worth noting. It's insulating, right? And what does that mean? It's a solid sphere. It has a radius A. Has a uniform volume charge density rho, and it carries a total positive charge big Q. We can have flux through insulating surfaces, sure. But we'll talk more about electric field lines and how they change when you have different types of substances, like plastic or that kind of thing, especially when we talk about capacitors. But for now, don't, so your question is there flux on an insulating surface? Just, you're kind of conflating two different ideas at that time. Keep in mind that this is saying there is an insulating sphere. It's not the surface that we're going to be talking about. The surface is, remember, it's may I say it's an imaginary surface? This is a real sphere. It's a real sphere, basically. It just happens to be an insulating sphere, which means... Well, you guys tell me, what does it mean that it's insulating while I draw it? What does it mean that it's an insulating sphere? What does that mean? What is an insulator? Charge couldn't pass through. The charges don't really move, basically, is the key thing. Okay? Charges don't really move around, right? So this one in particular, it says, has a uniform volume charge density, rho. What does that mean? That means that the charges are literally spread evenly throughout this object. Does that make sense? So if I wanted to go in here and put a bunch of positive charges, I would say that they kind of fill the entire thing. And in a given region, you're going to have a fixed amount of these, and it's just constant over our entire surface. But it's not just on the surface is what I'm trying to get at. It's also inside the object that you have these charges. The entire thing is just full of charge. Does that make sense? and you have some volume charge density, right? Rho. Rho is going to be the charge per unit volume. It could be like 1 coulomb per meter cubed or something like that. Or it could be like, you know, it's density, but it's just charges, basically. We also know that Q is our total charge, so the entire thing has a total charge Q. What else do we know? Its radius is A, so we'll indicate that the radius of this object is A. Okay. Step 1. Calculate the magnitude of the electric field at a point outside the sphere. Okay? Now, the way that we're going to do this now is we're going to use Gauss's law to solve for the field. Gauss's law tells us that the charge enclosed is equal to the surface integral of the electric field dot product with dA. Surface integral EdA is what the Q enclosed is equal to. And our goal here is to find electric field, right? We want to find what E is equal to. Which means we're going, this might look like this might sound challenging, I don't know. We need to pull this out of the integral, somehow. Turns out it's really easy to do. Okay? Part A says, calculate the magnitude of the electric field at a point outside the sphere. So how do you do this? If I want to use Gauss's law to solve for an electric field, and it says find the electric field outside the sphere, right? Let's get some room here. We're going to have to scroll down a little bit. That's fine, you can still read it. So what I need to do is I need to construct a Gaussian surface. A Gaussian surface is going to be some surface that in some way exploits our symmetry in the problem, okay? And that type of surface that we're going to get in this case, well, it's going to be based on electric field lines. So I need to kind of draw some electric field lines here. Now, I don't immediately know how a sphere is going to differ from a point charge in terms of field lines, but I think you guys would probably agree that it's not going to be that much different. Would you guys agree? The, oops, copy paste, there we go. I would say that the electric field is pretty much going to be the same on this object. And that, here, let me do like this, we'll go like this. So our electric field lines in this case are going to be pointing just like this. I don't even know what the fastest way to do this at this point is. Probably just do one at a time like this. Try my best to make them at right angles. So that's kind of what our electric field's going to look like, right? And it's going to point out and away. And I could draw more lines. I'm just going to draw 6 for now. Those all right angles? Yeah. But there's electric field lines that come towards you out of the screen. There's electric field lines on the back that go away from you out of the screen. There's electric field lines all along this thing, and they point out like little needles pointing out of a pincushion or something. You know, they're all pointing away from the surface, right? Okay. So now our goal is to use this equation, and how do we use this equation? Well, one of the things you have to do, kind of the first thing you need to do, is we need to select a Gaussian surface. We can pick whatever we want. You pick a Gaussian surface. So to do that, we're going to pick one that makes it really, really easy to do the integral. And Ash's question is, can we pick one that's concentric with the sphere? Why would you choose that? Why would you choose one that's concentric with the sphere? Why would you choose that one? We know the radius. Does that look concentric right there? It's pretty concentric, right? So you're saying pick one like that. All right. So we pick one of these, And we need to define the radius of the object that we picked. So I'm just going to draw in here and say the radius of our Gaussian surface we're going to call r. It goes all the way to the center right here. That is our Gaussian surface. I'll indicate that it is. Again, it is an imaginary thing. It's not something that's real in this case. It's just something that you've constructed to perform a calculation. Something that you've constructed to perform a calculation. All right. So I would argue that this is a good choice, and that a cube, for example, would be a bad choice. And as we do the calculation, hopefully it becomes clear to you. Once you've chosen your Gaussian surface, you want to draw, at any point that you can on that surface, the direction of your area vectors. And I would say your area vectors are going to point perpendicular and away from that surface. And then indicate the direction of the electric field at each of those locations, which we've already done with our lines here. That's our electric field, right? And then kind of just to verify, you go to every point and say, hey, let's just make sure, does the electric field actually kind of line up just like it does up here? And sure it does. Over here, the electric field seems to line up with the surface vector for the sphere, right? So everything looks kind of nice and dandy, and this allows us to kind of like look at the integral now. And our integral says q enclosed over epsilon naught is equal to the surface integral of E dot dA. And now we start making simplifications. The same simplifications, we will make these every time. If you choose your Gaussian surface right, all the steps I'm about to do will be the same in every problem you do. The first thing you note, E and dA, they're parallel to each other. Okay, well that means this just becomes E times dA. And then I say, does the electric field change as I go to each of these positions around the sphere? And I would say, no, it doesn't. It's the same everywhere, certainly. How could it not be? After all, I've put a sphere around a sphere, and I could rotate my sphere on the inside, or I could rotate my Gaussian surface on the outside, and you wouldn't know the difference, right? It would just, everything looks the same, no matter how you rotate it, as long as you keep them both on the same center. That means the electric field's the same everywhere, so we have to pull the electric field out of the equation. And then we have just integral EdA, and then we say, okay, well, the integral of dA we said already is just the surface area of our Gaussian. Well, how big is the Gaussian? It's 4 pi times the radius of the Gaussian squared. And now r is actually a variable. We could have made the Gaussian to be as big or as small as we wanted to. The left-hand side of the equation says to add up all of the charges that are actually enclosed within your system. Well, we know that inside of our Gaussian surface, we've already enclosed the entire charge of our sphere, right? So this just becomes capital Q over, and now we can divide this piece to the left-hand side. And we've basically done in reverse what we did before. This is only going to be true for r greater than a, by the way. Because we're going to have a different answer once we go inside. And there it is. You get the result that it doesn't matter that it's a sphere. Once you're outside the sphere, it actually acts like a point charge, right? You get the exact same result for a spherical object that carries charge once you're outside the sphere. And notice that, we could have made this Gaussian surface... Whoa, I didn't mean to move it. Oops. Oh, no. Maybe, like, right there? This is a lot easier to put in here when I didn't have these other things to line up. There we go, that's better. So, this Gaussian surface could have been larger, right? It could have been smaller. So r is effectively a variable now. The radius of the sphere does not show up in this equation, except that it's the boundary. And there you go. You know what this also tells you is that you could figure out the value of the electric field right on the surface with this too, right when you're right up next to it. And it would still have that same notation. Okay, what about inside? That's what's next. Do you guys have any questions about what we just did? All right. In order to make things a little cleaner, let's start over again down here. And let's also make it bigger, because we're going to go inside now. Here, select everything. Zoop. Okay, now we're going to draw a Gaussian surface inside of our object. Okay? Because that's what part B says. Part B says find the magnitude. Put it right here. Find the magnitude of the electric field at a point inside the surface. Okay. So again, our first thing to do is to draw a Gaussian surface. Now, I'll ask you guys again, do you want to draw a cube inside of here? Hopefully not. That would be extremely complicated. Maybe you don't appreciate it as much yet. You certainly will when you start looking at some of the homework problems. So instead of that, let's just do what we did again. Let's draw a circle inside of here. What did I use? Green for Gaussian? Yeah. Green. Shape. So this is going to be my Gaussian surface now. I'll do my best to center it there. I think you guys will probably be okay if I just delete this piece here. I don't think we need that anymore. We can just kind of treat this as like a two-dimensional system at this point. It's not two-dimensional, but probably a little easier to read it that way. Okay, so now I've got my new Gaussian surface, right? That green, this green thing here, and maybe it helps if I just indicate that it's a Gaussian surface, because yeah. So that's our Gaussian surface now. Now I'm drawing it inside of our surface because, after all, that's the place where we want to find the electric field. That's kind of our goal here, and this can easily be missed as I'm saying this. Our goal is to find the electric field. So I want to make sure that I put my Gaussian surface at a place that can kind of like probe the electric field, you might say. So there's my electric field, arbitrary radius r, where r is less than a, right? And so that's our Gaussian surface right there. Okay, again, we need to perform the exact same mathematical operation we did before. We have to do charge enclosed divided by epsilon naught is equal to the surface integral of E dot dA. Now, to do this, we look at the right-hand side again and we say, oh, we have to do this EDA thing. So I better get to drawing my dAs. So what do my dAs look like here? Well, it's a surface again, right? So it's a spherical surface again, so the dAs are basically the same as they were before. That certainly didn't change. Okay, and the next piece, and this part is a little more tricky, I guess. We have to ask the question, well, what direction does the electric field point here? And I would try to argue that there's really no reason for us to believe that the electric field should point off at some random direction like this, right? It told us that the charges were uniformly distributed throughout, right? In order to have an electric field that kind of points off to the left, I would need to have, like, would you guys agree, more charges on the right side than I do on the left side? Would you guys agree with that statement? In order to have an electric field that points like the one I've drawn here, I would have to have more charges on the right side than the left side. Does that seem reasonable to you guys? But we don't. So the electric field has to basically point. There's only one place it can point if this is a truly uniform distribution, and it has to point basically parallel to the surface that we've drawn. In addition, because it's a spherical system and there's so much symmetry to spheres, we have no reason to think that this electric field would be any different than this electric field, right? Like, we could just rotate the Gaussian surface by 90 degrees and you'd ask, why would it change? You know? It's a sphere after all. It needs to be the same in all directions, right? So what does that mean? That means that we go through, and this is hopefully starting to get repetitive enough that you know what I'm going to do next. What do I do first? I say this thing is just EDA. You could literally skip all these steps if once you've done this a few times. And then you say, oh, well, E is the same everywhere. So we pull that out of the integral. And then we say, okay, well, we're just left with E times the surface and the surface again, as is 4 pi r squared. Okay, it's literally exactly the same thing. All right. Will the charges be less because there are less plus inside the small sphere? 100%. Yeah, this is the part that's going to change. That's right. Q enclosed. That's what's going to change, right? So that we need to figure out, right? That's almost its own calculation. We need to find out how much charge do we actually enclose within the surface. Maybe you guys can figure it out. How much charge do we actually enclose? You immediately think of volume. Why is that? Volume density. Volume times density. Yeah, exactly. The charge enclosed should be equal to the volume of that sphere, the volume, specifically the volume of the Gaussian, right? Multiplied by our charge density, rho. What is the volume? Well, the volume of the Gaussian is 4/3 times pi times r cubed. What's the density? We know that the total charge on our object is big Q. And we also know the whole volume of our object. What is that? Well, it's a sphere with surface, or with radius a, so the volume of our entire object is 4/3 times pi times a cubed. A bunch of stuff cancels, and what I end up getting, I'll write up here, which is going to be Q times r cubed divided by a cubed. Q times r cubed divided by a cubed. So what's E equal to? Well, E then is equal to r cubed and r squared cancel. So we end up getting, let's see, 4 pi. Oh, I left something out, didn't I? I left an epsilon out. There we go. Epsilon naught. Okay, what do we get? So, let me undo one more thing. There we go. Epsilon naught. All right, so we're going to have, let's see, Q over 4 pi epsilon naught a cubed times r. And this is going to be for the region where r is less than a. That is the value of the electric field inside of a uniformly charged solid sphere. And it has to be insulating. Otherwise, these charges could not stay where they are. And that's one of the things we're going to learn next time. Change this to a conductor, the whole thing changes. And one of the things we'll derive is that the electric field inside the conductor has to be 0. And all of the charges have to go to the surface. But not in this case, it's an insulator. And this is the answer. For r less than a, you get that. Notice that these are all fixed values, right? Q over 4 pi a cubed epsilon naught is basically just a bunch of constants. And so the only variable here is little r. So that tells you that the electric field is basically just linearly increasing as you go to larger and larger radii here. And r is a variable here too, right? So we can plot, and this is the thing that I had over here. We can plot right here what this looks like. We've got the electric field inside and outside. So when I plot them, it's going to look something like this. See if I can get this to where we can kind of see all this stuff together. In the region 0 to A, and here's your sphere, right? In the region 0 to A, that's the electric field. In the region from A to R, that's the electric field. Now they've used K and I've used epsilon naught, but they're the same thing. This thing is K in the numerator. So there you go. You guys have electric field calculations just like this, except with one change, which is the way you're going to calculate the Q enclosed is going to be a little different. And I want to mention something about that so that when you see them. But before we do that, do you guys have any questions about Gauss's law? Questions at all? Picked a bad time to lose my pen. Oh, there it is. So that's our introduction to Gauss's law. I think I might do one more of these problems actually for you guys. Any questions? Is it interesting to you guys? So the thing that I want to mention here, in general, in systems like this, if I want to find Q enclosed, what you're going to do is you're going to integrate the charge density with respect to the volume. What does that mean? Well, I guess I'll let you guys figure out in general how to do this, but I can tell you that if you have a sphere, that for a sphere what this is going to become is like integral rho times 4 pi r squared dr. That's for a sphere. And if you're doing something with cylinders, it's going to become something like a little bit different. And I'll let you guys work on how that's going to work out. You may know some things from your calculus class that help you out with that. You have a homework problem where you have to do this. And I know it showed up on some of my exams in the past too. If you do this integral and you use the charge density that we used in the problem, you'll get the same answer. All right. Any questions? Let's do this one. All right. A cylindrically symmetric charge distribution. Find the electric field at a distance r from a line of positive charge of infinite length and constant charge per unit length, lambda. This is a problem we've already technically done, but we're going to do it using Gauss's law. So I've got a line. It goes on forever. So I've got a line, and it has a certain amount of charge per unit length, but it extends up and down forever. It's infinitely long. Okay. The object is positively charged, let's say, and it has a fixed amount of charges per unit length. So it's positively charged, let's say, and has a fixed amount of charges per unit length, lambda. Okay, so lambda, that's basically your charge per unit length. Now, I need to figure out a way to use a surface to find what the electric field is at some distance r away from this object here. That's our goal. What is the electric field at a distance r away here? Now, it's an infinitely long charge, and from some stuff that we did in the previous chapter, you guys may remember that the electric field that's produced by such an object basically is just a bunch of lines that point radially out like this, right? Bunch of lines that just point out radially like this. Why won't it let me control select these? It's really weird. Picked up some of the charge there too. Didn't mean to do that. Yeah, something like that. You've got electric field lines. They kind of come out like this, right? And they come out on the other side too, right? You've got electric field lines on the left-hand side, and they're going to point off in that direction. Not going to make these nearly as straight, but I guess we'll just deal with that for now. So you're going to have electric field lines. They're going to point radially out from this object. You can imagine drawing more lines here. You can also imagine that if you rotate the picture that I've drawn here 180 degrees around, that's going to sweep out the direction of the electric field lines. They're all pointing out like spines away from this line that's drawn right here. All right. So the question would be, how do I choose a Gaussian surface for this scenario right here? And kind of within the name of the problem is a hint at what you want to choose. We're going to choose a cylinder. All right, so we're going to surround our object with a cylinder of radius r. Okay, so we're going to have the top of it's going to be like right here. And I'm going to make the bottom of it somewhere down here. And then I'm just going to use lines to connect the sides. So this is going to be our Gaussian surface now. We're going to indicate that the area of the top is going to be A, the area of the bottom is A, and then we're also going to say that the length of our object is L. Next thing we're going to do is we're going to come to the points on the surface, like we did in previous problems, and say the area element here would point like this, the area element here would point like this. That looks good because all the area elements are the same. If I come to the left-hand side, we're also going to have area elements pointing this way, parallel to the electric field. That's good as well. If I was to come to the front of this surface, I would have an electric field pointing out of the screen towards you, and I would have an area element pointing in the exact same direction, right? But if I come to the top surface, now my area element basically points straight up like this, right? And on the bottom surface, the area element also points in the same direction. This is also okay because the electric field at these locations is going to be at a right angle to it. The electric field down here is going to look like this, and the electric field up here would look like this and like this. So there's going to be a right angle right here. That means that we can very quickly solve for the electric field by using Gauss's law. Do you guys have any questions about what we're doing here? All right, in solving this problem, we're going to break our surface into three different parts. We're going to find the flux through the top, plus the flux through the bottom, plus the flux through the curved part, okay? And since this is equal to flux, I'm going to write it like this. We're going to write it as flux through the top plus flux through the bottom. By top, I mean top and bottom. And then plus the flux through the curved side. I would argue the flux... Well, you guys tell me. What's the flux through the top going to be? For this infinitely long line of charge. Top and bottom is 0, right? So we'll just say that's 0. And that's 0. It didn't change colors, whatever. The flux through the curved part is going to be... this. And so the curve becomes just that piece right there. And for the curved part, we just noticed that E and dA are parallel to each other, so we can just change it to from a dot product to just EDA. We'd also could make the following statement: as long as the object, the charged line lies along the central axis of the cylinder, the electric field should be the same here, 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 etc. Because I could rotate my Gaussian surface and it wouldn't change the way it looks, right? So that means that the electric field's the same at every single point. Because there's symmetry to it, right? And you're just left with this. I mean, do you notice how the steps for these have been basically... other than this step right here, where I said, oh, top and bottom, don't have to worry about it. You notice the steps for these Gauss's Law problems are 100% the same every single time. You start from this, you change E.dA into EDA, you pull the EA out because it's constant everywhere, and then you integrate the surface. Now, it's not a circle this time, so what's integral dA going to represent now? 2 pi RL, that is right. It is going to be the surface area of the curved portion, which is 2 pi times the radius, and we multiply that times the length L. Alright, perfect. We've finished the right-hand side. We can't do anything more. Our goal is to find E. Yes, Ash, that's the right answer. Because E and dA are the same direction, the angle between them is 0, so we know that E.dA basically just becomes EDA. Now this is the next part we have to deal with. You guys tell me, how much charge is actually enclosed by our surface? How can we figure that out? How much charge is enclosed? It's not infinite. The line is infinite, so the total charge on the line might be infinite, yes. But we've only closed off a portion of the line. This has a fixed length here, right? What can we write down for the charge? Well, the density of the charge is one thing, but we need charge, so it's going to be related to density. Sure. But yeah, lambda L. That's right. Q enclosed is going to be lambda times L. Except not like that, because I made the L look like that, right? You take the charge per unit length, let's say it's 10 coulombs per meter, and let's say that this is 2 meters long, you'd have 20 coulombs, right? You do 10 times 2. If this was 5 meters long and lambda was 10 coulombs per meter, so if it was 10 coulombs per meter and this was 5 meters long, you'd have 50 coulombs, right? So that you get the idea that you're just basically doing lambda times L over epsilon naught. That's how much we have enclosed. Come all the way down to this line right here. Let's scroll down just a little bit so we can get the final answer. We see that the L's cancel out, and what we end up getting is basically that the electric field is lambda. God, that looks awful. The electric field ends up being lambda divided by 2 pi epsilon naught, and then there's a 1 over r dependence like that. That's the value of the electric field, and we can go one step farther and say, technically, if we want to turn it into a vector, this is going to be a radially symmetric system, so we can put the lambda divided by 2 pi epsilon naught times r, and we can multiply by r hat. Because after all, r hat points like that. And there we go. This is a result that we derived by using a lot of calculus in the previous section, but in tonight's class we did it in probably way more lines than we needed to. We could have basically skipped... Where's my mouse cursor? Where did it go? I can't find my mouse. Okay, well, whatever. Oh, there it is. we really could have done this in like 2 lines. We could have started from this line right here. See, we're just loading page sync access. What is this, hosted online or something? Whatever. So yeah, we could have skipped a lot of steps, is my point. I just went through more to make sure you guys saw the details, and the details are actually kind of boring. No, in this case, the top and bottom flux is 0 because none of the field lines actually pierce through it, or you could say that the electric field line is perpendicular to the surface. It'd be like, you know, one thing, like, flux is kind of like looking in a mirror. You know, if you tilt the mirror on its edge, so you're looking at the edge of the mirror, you're not going to see your reflection, right? But if you put the mirror like it normally is, you see your reflection. It's kind of a similar idea. If none of the rays of light actually hit the mirror, you won't see anything. If none of the electric field lines go through the surface, you're not going to get any flux. Okay, so that answer your question? Yeah, no problem. Okay, that is a long video right there. That's an hour and 15 minutes, so I'm going to stop the recording. If I can find my mouse cursor.